All right, so today we're going to look at section 10.1, parametric curves. We're into chapter 10 now, and as before, this is really very distinctly different than everything else that we've done before. We no longer have Taylor series or Taylor polynomials or anything like that. It's really just a new topic, and the idea goes as follows. Our goal here is to describe curves which are not functions in the general sense. All right, so maybe we want to describe a curve which describes the flight path of a bug through space, or the path of some particle in space if this particle is subject to some forces, and we want to see where it goes and describe where it goes. But this isn't a function because it doesn't satisfy the vertical line test. If I input this value for x, then I get, in fact, 3 different y values. So it's not a function. And not only that, we want to do better than just describe where the particle is. We want to describe where it is and when it's there. Right? So describe 2 things, where and when. Right? So we're going to describe this motion in terms of time. So we're going to think about this as follows. We're going to think about time, which is a variable t. We're going to take this variable t and we're going to use that to describe a point. And let's call that point P, which depends on time t. So t, we input t and it outputs a point, P at t. So we input and we output this point P at t. As time changes, the point changes. Now a point has an x and a y component. So there's an x and a y value at this particular point. But if the point depends on time, then x and y both depend on time. So we can think about this as x at t, y at t. And already we're at the basic idea of parametric curves. And so if we think about time t and we think about x varying with time and y varying with time, then putting those together gets me an x and a y point which vary with time, which get this point that varies with time as well. And so really all that we have in a parametric curve is we've got 2 functions, an x curve and a y curve, both which depend on time. So this is what we got. So a parametric curve is really a pair of functions. Is really an x at t and a y at t, which when we put together make a curve by describing motion through space. So this is our idea. And so what we're going to do is we're going to look at a couple of basic standard types of parametric curves, see how they fit together to describe a path through space and what that path is. Right, so let's look at this first one. Suppose that I have the parametric curve x of t is 2 plus 3t, and y of t is 1 minus t. And so this is input time. It gets me an x coordinate and a y coordinate that depend on time. As time changes, my point changes, so I'm describing a path through space. All right, so let's just understand a few things about this. We can really start at any time, and we're going to allow time to be negative as well. We're going to input any t value, so minus infinity is less than t is less than infinity, and ask what shape does this make if we were to plot it. Let's just pick t equals 0 as a baseline, as a placeholder to start. If I plug t equal to 0 in, then I get x is 2 and y is 1. So t equal to 0, then xy, t, then the xy point is 2, 1. So that's where we are time 0. At time 1, At time 1, well, we're at the point 2, 1, but then we've adjusted things. The x value after time 1 moves up 3 units. So the x value moves up 3 units to 5. And the y value actually moves down 1 unit to 0. And here we are. So that's where we are at time 1. At time 2, what happens? Well, we still started at 2 and 1, but at time 2, now the x coordinate is 6 units up. So as time goes forward, our x coordinate is moving up 3 units per unit of time. So in fact, what happens is we move forward another 3 units in the x direction, and then down another 1 unit in the y direction. And we get the point 8 minus 1. X goes up another 3, y goes down another 1. And hopefully you can see what's happening here. And so if we put this all together, if we continue to go, we're going to go across and down 1, across 3 and down 1, across 3 and down 1. And if we put it all together, we're going to end up making a straight line. And a straight line, and the slope of that line is the rise over the run, but the rise was minus 1, and the run was 3, which we got right from here. Right, the minus the y over x. Okay. So this shouldn't be a huge surprise because we started with a linear equation for x and a linear equation for y. We put them together and we make a line. Notice a few things, right? This is more than just the sum of its parts, right? So if I look at everything, I get a straight line, but not only that, I can say that this line is, I can give it a direction in which it's being traversed. This line goes this direction. As t increases, the line goes down, right? So that's the direction that the curve is taking. And not only that, remember we have, I wrote this wrong, that should have been a 0. T equals 0 is right there. This is t equal 1. So it tells me where I am and when I'm there. All right. So let's go the other direction. Parameterize the line segment from the point 1, 2 to the point minus 3, 4. Right, so in terms of a picture, I'm starting at 1, 2, and I'm going to minus 3, 4. That's where I need to end. Right, so that's the goal. I want to go from here to here. I'm gonna say that I want this to be t equals 0, although that's not going to be necessary. But what we do will make this pretty simple. I'm going to say that I start at this point at time 0, and I end at the end point at time 1. And let's see what happens. All right, so I need x at t, and I need y at t. If I want x at t, if I want time 0, so this is going to be something plus something t, and something plus something t, just like we had before. Linear for x, linear for y, put them together, and it makes a line. Now, when I plug t equals 0 in, I need to be at the point 1, 2. So if I plug t equals 0 in over here, that's going to go away, and that's going to go away. So that had better be 1, and that had better be 2. Finally, what's the slope of this? Right? So the slope of this line, the rise is actually 2, and the run, because I went up 2 units, and the run was actually backwards 4 units. And let's write it like this. The slope was rise over run, which was 2 over negative 4. And so where did we get that? We got that from taking the difference, right? So that's 4 minus 2, and that's minus 3 minus 1. The end point minus the beginning point. And we get a 2 over minus 4. And I'm just going to put these in for the coefficient of t. The y is the rise, so I'm going to put a 2 right there. And the run is the x, so I'm going to put a minus 4 right there. And if we put this stuff together, as I have done, then when I plug t equal 1 in, if I plug 1 in for t, this is minus 4, so 1 minus 4 makes negative 3, and 2 plus 2 makes 4, just like we needed. So this is the solution. Okay, so let's look at this one. X of t is cosine t, y of t is sine t. Let's start by making a chart as before. At time t, what's the point? And let's start with 0. At time 0, when I plug 0 in, I get cosine of 0 and sine of 0. Cosine of 0 is 1, sine of 0 is 0. Now what are we going to plug in for t that makes sense since we're doing trig stuff? The t values that we're going to be able to get nice responses for are not 1, 2, 3, and 4, but rather versions of pi. Since cosine of pi makes sense, cosine of pi over 2 makes sense. So let's look at that. What happens if I plug pi over 2 in for t? Well, cosine of pi over 2, we're thinking about a unit circle. Pi over 2 is 90 degrees. Cosine is the x value, and the x value there is 0. The y value there is 1. At pi. Now we're at 180 degrees. Cosine here is minus 1, and sine is 0. At 3 pi over 4 over 2, that's 270. The x value is 0, and the y value is minus 1. If I went to 2 pi, I'd get 1, 0. So at time 0, we're at the point 1, 0. At time pi over 2, we're at the point 0, 1. At time pi, we're at the point minus 1, 0. At time 3 pi over 2, we're at 0, minus 1. And at time 2 pi, we're back to here. That shouldn't be too far of a stretch to say that actually what we're doing here is actually just traversing this unit circle. We're going around the unit circle in a counterclockwise fashion, and really it recreates our unit circle that we were thinking about from trigonometry here. Now, what's the equation of this circle? X squared plus y squared is 1. That's the equation of this circle. What happens if I plug in for x and y? Well, cosine squared t plus sine squared t does in fact equal 1. So I can tell that a particular parameterization matches a curve in terms of x and y by plugging in for the parameterization, by plugging in the x and the y functions and seeing that the equation actually holds. Okay, let's look at another one with the circle. Suppose that we change things a little bit. Suppose that x of t instead was negative cosine t, and y of t was still positive sine t. Well, what changes? Well, this still has x squared plus y squared is cosine squared plus sine squared is 1. So this still is the circle, because the x and the y's fit the equation x squared plus y squared equals 1. All right. However, there's something different about it, because what happens if I go through if I start at t equals 0, if I start at t equals 0, I actually end up getting negative 1, 0. And then if I go through my t, so if I put pi over 2 in, then I'm going to get 0, 1. at pi, then I'm going to get 1, 0. Because cosine of pi is -1 and -1 is +1. And so on and so on and so on. And now we can see what's happening. At time 0, I start here. I go around the unit circle, but at time pi over 2, I'm up here. So I'm actually going in this direction. So now I'm starting at this point over here on the left-hand side of the circle, and I'm traversing clockwise rather than counterclockwise. So although this parametric curve makes the same points, goes through the same points, it's a different curve because I started at a different point and I'm going in a different direction. Finally, let's look at one other type for right now. If let's parameterize the curve y equals x squared. So this is our parabola. Let's parameterize that, and let's say from the point -1, 1 to the point 1, 1. So I want to go from here to here, and I want to go in this order. I want to go in this direction. So that's my curve. So I need an x at t, and I need a y at t. Well, here's the trick. If I have a function, we can always turn it into a parameterization in a relatively easy way. But I can traverse through this curve by just letting the x at time t be exactly t. So I'm going to say I'm going to move through here so that the x value changes exactly as time changes. And if I let x at t be t, then since y is x squared, in order to make this curve, I want y to be t squared. So that then y is in fact x squared. It matches our curve. The last part is to figure out what t's to use in order to go from the points that we have, the points in question. This occurs when x is -1, but x is t, so this is -1 for t, and this occurs when x is 1, which is the same thing as t is 1. So this is an appropriate parameterization. And that's what we got for the basics for parametric curves. See you next time.